Hello, my dear friends. Welcome back once again to the JCE Connect. So, in the last session, we have solved one problem, that is over compression member. How to evaluate the design compressive strength of a given section. We have solved 2-3 types of problems. In the last session, we had solved one problem, that is two channel sections back to back. Okay, and in that they are given two conditions, that is if the channel sections with cover plate and without cover plate. I think this was the problem what we have solved in the last session. Okay, they are given two conditions, that is without cover plate and with cover plate of size 500 mm by 10 mm. So in the last session we have solved the problem over without cover plate, two channel section back to back with a spacing of 280 mm in between and without cover plates. Okay, and in today's session we are going to solve how to calculate the design compressive strength or the design compressive load for channel section with cover plate. Okay, so here we have the sketch. Calculate the design compressive strength. Okay, understood. So we'll start with the solution. So I'll just brief out the sketch here. So you can see here we have two channel sections back to back with a distance of 280 mm, and these two channels are again composed with two cover plates at top and bottom, that is size of 500 mm by 10 mm, means 500 mm length and 10 mm in thickness. Okay, so we have to check, we have to find out what is the increase in compressive load by addition of these two cover plates. What is the difference of compressive load, okay, by addition of cover plates. Okay, so we'll start with the solution now. So we'll note down the required properties. Okay, so first of all, the area of this section is we have two channel section, two plates, so that is 2 times, that is for channel 6293 plus 2 times 500 mm by 10 mm. Okay, so we will get the area as 22586 mm square. So this is the total area. That is 2 times channel section plus 2 times the plate. We have what? Okay, then we have to find out moment of inertia also. Next is moment of inertia. Okay, moment of inertia, that is mi. We have to find out the moment of inertia mi, that is Ixx and IR. So we will calculate on the, so that is Ixx is equal to, so here we have to find out Ixx, that is for I for channel and I for plate. Okay, C stand for channel, P stand for plate. So we have to combine here because we are using channel and plate both. Okay, so that is so we'll calculate on down. So the I for channel and I for plate. So that is channel section, it is directly 15082.8 into 10 to 4. Okay, into 2, because two channel sections are there, and with respect to horizontal axis, that is xx, the centroid of the channel section and the main centroid is coinciding, so no need to again I plus ah square. So here I plus ah square will become 0. So here I plus ah square will become 0 because h is 0 here. Now for plate, so plus area is I plus a square. So the basic formula I'll write here, I plus a h square. So in channel section h is 0, so that's why I have to write only I. A into h will become 0. Okay, so for plate now, with respect to horizontal axis, this is B and this is D. Okay, so B is 500 and D is 10, that is BD cube by 12. I plus A is 500 by 10 into H, that is from the horizontal axis, the distance from the horizontal axis to the center of this plate, that is h. So horizontal axis, so this total is how much? 500 from here to here. So this total from here to here is 500. Okay, this is 500. So 500 divided by 2 is 200, and this plate is 10 mm divided by 2, because from center of this to center of this. So 200 plus 10 by 2, so that is 205. 205 square, I plus a square. So calculate here. So we have got that as 721.98 into 10 raised to 6 raised to 4. Okay. Then next is IYY. Okay, IYY. So again it is for channel and for plate. So by using formula I plus a square. Okay. So for this thing, okay, for channel we have calculated IYY already in the previous session. So I'll note down the same formula, the same value, that is 349.43 into 10 raised to 6. If you go back and check IYY for channels we have calculated, so that is we have got 349.43. We have noted down directly. So this is for channel, plus again here you have to multiply 2, a I plus a here into 2, because again we have two plates, I plus a square. Okay. So then is for next for plate again. So with respect to vertical axis, so B is 10 and D is 500 now. So B is BD cube by 12, B into 500 cube by 12, I plus A is 500 into 10. Now H is with respect to the vertical axis. You can see, अब यहाँ पे देखोगे ये वर्टिकल एक्सिस हमारा है and the center is also coinciding, so H will become 0 here. Correct? Our vertical axis, the main vertical axis of the section, and the centroid of the channel section with respect to this, both are coinciding, so H will become 0. Okay. So by this you got IYY as 557.76 into 10 raised to 6 mm raised to 4. 557.76 into 10 raised to 6 mm raised to 4. So therefore I minimum is equal to, we have to take the minimum value between these two, I axis and I minimum is equal to IYY. So that we have got 557.76 into 10 raised to 6 mm raised to 4. We got I minimum as IYY. Okay, understood? Now next is R minimum, that is square root of I minimum by area. Square root of I minimum by area. So that is I minimum is IYY. So we have got 557.76 into 10 to 6. Your area is 22586. This is again square root. Okay. So you got it is as 157.14. So you get this as 157.14 mm. You got R is equal to 157.14 mm. So therefore, next, slenderness ratio lambda is equal to KL by R minimum. KL by R minimum. So it is as K is 1, length is 6000. Not K, because directly KL, the effective length is given here. No need to here direct. Sorry. So directly effective length is given, that is 6000. Divided by R minimum is 98. Sorry. Here it is we have got 157.14. So check how much you get. Okay. So L is the effective length, directly it is given 6000 divided by R minimum we are calculating, so 157.14. So with this we got it is 38.18. So we got the slenderness ratio lambda is equal to 38.18. Now how to go back to again compressive stress table. compressive stress table. So before that, we have to find out the section, given section is fitting in which class. Okay, as I told you in the previous session, we have to find out the buckling class of this section. So for that, you have to go back to the again table number 9C. Okay, wait, not table number 9C. Okay, table number 10 you have to go for. You have to go for table number 10. Okay, आप यहाँ पे देखोगे. Okay, table number 10. So again, it is channel section, or it is a built-up section now. If it is a single channel section, no problem, buckling class C. If it is a double channel, double I, whatever, built-up section, so we have to take it as a built-up section. So for that also, you have to take it as buckling class C only. You have to take it as buckling class C only. Okay. It is very difficult to show it here. Okay, you have to take buckling class C only. Okay, 1 minute I'll show you. Like this I can show you. Okay, you can see here it's a built-up section. So it is C. Two channels back to back, so it is not a single section. You can see it's a built-up section. So you have to go for buckling class C. So you can write right here. Therefore, again, the section is in buckling class C. The section is in buckling class C. So therefore, referring, you have to refer table number 9C. Okay, so refer table number 9C. For that, then I'll just note down the values. If you go back and if you check table number 9C, so you have to note down the values for lambda. So you have to interpret again here for lambda 30 and 40, and here we have the FCD value, so that is 211 and 198. Okay, understood. So we have to got 38.18 we have to get. Okay, so after interpolation between these two, for 38.18 we will get FCD as 200.366. Okay, so therefore our FCD value is equal to, which is nothing but FCD. Okay, so therefore the design compressive load P is equal to FCD into area. So FCD is 200.366 into area is 22586. We got this as 3758 kilometer. Okay, so we got P is equal to 3758 kilometer. So with cover plate we got the load as 3758. Okay, so once we'll check without cover plate how much you got. Okay, if you check that without cover plate, I think you have got it as C. You have got it as 2512 kilonewton. Without cover plate we have got it as the P as 2512, and now it is 3758, means almost 1200 kilonewton increase in the load carrying capacity. This is 2514, 2500 we consider, and with the cover plate if you take, see, with cover plate if you take, it is carrying 3700, means almost 1200 kilonewton load is increased by addition of two cover plates. So this we have to observe by addition of cover plate, what happened and what was the behavior, and without addition of corporate, what is the change in the load carrying capacity. Okay, so this is regarding today's session. So in the next section we'll have another types of problems. Okay, then so this is the end of the today's session. Okay, thank you. So in this next problem we'll solve with again to find out the design compressive load of the column made up of four columns, the column made up of four angles at the corners, and the column size is, the angle size is ISA 100 by 100 by 10, and the column size is 400 mm by 400 mm. Okay, so the total column size is the square column 400 by 400. Okay, and the column is made up of four angles at the corners, ISA 100 by 100 by 10, 100 by 100 by 10, and the other given data are the length of the column is given as 3 meter, and the end condition both ends are hinged, so therefore K is equal to 1. The effective length factor K is equal to 1 when the both ends are hinged. You can easily get that from IS 800. Okay, and therefore the effective length is equal to nothing but K into L. Okay, that is effective length factor is 1 and the length is 3 meter, so that is we have got as 3000 mm. Okay, so this is these are the given data, we have got it from the given problem. Okay, so next is we have to find out the moment of inertia again. Okay, so that is moment of inertia. So here both the angles are both the legs of the angle are same, so nothing but it is a equal angle. So Ixx and Iyy will remain same. Okay, both the legs of angle are same, so Ixx and Iyy remain same. I can show you in the steel table. Okay, so if you go equal angle, I can show here, you can see here for equal angle, you can see here equal angle, rolled equal angle for 100 by 100 by 10, I can show you that is 100 by 100 by 10. Okay, you can see, and here you can check the value of Ixx and Iyy here. So for 100 by 100 by 10, the value of Ixx and Iyy is it is 177. So the value of 100 by, yes, correct, it is 177. If you go and if you check in the steel table, यहाँ पे देखो it is Ixx Iyy. So if you check 177, yes, so it is both the values are same Ixx. So again we will calculate the by using again same I is equal to I plus AH square. Okay, so I is same here, so it is we have got 177 point 177, it is total 177 into 10 raised to 4. Okay, plus area of 100 and 110 is 1903 into I plus A. Now H, it is very important to calculate H here. अभी यहाँ पे देखो, so here the centroid of the single angle is somewhere here, like if I draw this thing, this is the centroid of the single angle. Okay, now H is nothing but the center of the main, the centroid of the main compression member to the center of the angle, means here we will get this is as H, this value is H. Thus from the center of the main the main centroidal axis to the centroidal axis of the single angle. Okay, so if you check here, यहाँ पे देखोगे, okay, here you can see it is somewhere here, it is outside of this section, you can see horizontal axis and vertical axis, so here it is. Okay, so that is for value is nothing but Cxx and Cyy. So you have to refer these values Cxx and Cyy. So for 100 by 100 by 10, the value we will get it as, for 100 by 100 by 10, the Cxx and Cyy. So you can see 10, we have to go ahead. Yes, this value is Cxx Cyy. So that is at 28.4. Okay, so this value as, we have got it as this value as 28.4. okay, this value is 28.4. so I plus a square, I plus a, h is, see, this total is 200 now, this is 200, 200 minus this, so we will get h, 200 minus h is 28.4 square, I plus a square multiply by 4. Why auto multiply by 4? I will show it here. I plus a, h is 200 minus, so this total is 200, 400 divided by 2, so 200, 200 minus this 28.4, 200 minus 28.4, h square, so square into 4, 4 number of angles are there, so we will get this as I'll just we'll see when calculate, we will get it as 231.22 into 10 raised to 6 and 1 raised to 4. okay, so next, radius of gyration r is equal to square root of I by a, I is 231.22 into 10 raised to 6 divided by area is 4 times 1903, so we'll get it as, this value as 174.28. okay, 174.28 mm. so therefore lambda is equal to KL by R minimum. okay, KL is 3000, R is 174.28. okay, so we'll check, so this value will get it as lambda as 17.21. okay, lambda, that is slenderness ratio 17.21. okay, so now again we have to interpolate, you have to go back to table number 9C because it is a built up section. For a built up section you have to refer again table number 9C, so we have to interpolate for 10, 20, and so for 10 the value is 227 and for 20 it is 224, so we have to get for 17.26. so to find out the FCD. After interpolation we have to do the interpolation, so after interpolation we will get this value is 224.83 Newton per mm square. So therefore PD is equal to FCD into area, so FCD will get it as FCD into area 224.83 into area is 4 times 1903, so we will get it as PD is equal to, so we will get it as it is 1711.45 to 10 raised to 3 Newton or 1711.45 kilonewton. So this is the final answer with for a given problem, that is 4 angles at the corners for a column size of 400 by 400. okay, so this type of problems you may expect in the exam, small problems. If you get unequal angle, then there will be some change here. So what is the change? If you get unequal angle, you have to calculate I axis I y separately, because in case of unequal angle I axis will not be equal to I y. okay, so you have to calculate both the values separately. okay, this is regarding the today's session.